Hi everyone, welcome to tutorial 83 of our introductory Python for image processing tutorial series. In this video, let's learn about how to use traditional machine learning for image classification purposes. In fact, in the last 4 videos, we looked at using traditional machine learning for image segmentation purposes. Now, 2 things that we need to define here. Traditional machine learning, by that we mean using anything that's non-deep learning. It could be random forest, support vector machines, or anything else that's not a deep learning or neural network based approach. And by segmentation, we mean semantic segmentation. Every pixel classification. So here is a quick example of what we have done in the last 4 videos. We took an image and corresponding labeled image, which we call mask, and you can go to appear.com to create your own labels. And we took this as the ground truth, and we extracted a lot of features from our input image. And how did we do that? By applying a Gabor filter, Gaussian, median, Sobel. You can apply a whole bunch of filters depending on the complexity of the image. And the extracted images or the filtered images are the features that we are going to use as inputs to our machine learning classifier. That could be, again, random forest or support vector machine. So the key difference between image segmentation and image classification is that image segmentation refers to every pixel classification. Image classification refers to the entire picture classified as something. So if you're working with biological, or let's say infected cell image versus uninfected cell image, right? So this entire image, I'm going to take it and say, okay, this is infected. An entire image is why it is infected, like show me the areas that are different. That falls into segmentation, because now we are talking about pixel level information. But here we are talking about image level information. In this example, is this a barn, or is this a dog park? Is this a landscape, or is this a sunset? The entire image is classified into one of these 4 groups. So that's the only difference. So the label in this case is not at a pixel level, but at an image level. I'm calling this entire image barn. So as you can imagine, our labels are just barn, dog park, landscape, and sunset in this example. Again, it could be, if you are working with geological or material science type of samples, it could be texture 1, texture 2, texture 3. All of those textures may refer to iron oxide or something, but then they have different textures. So you can classify images belonging to multiple textures. In biology, I just gave you an example, malarial, infected versus uninfected cell. And it can be multi-class classification, or I should say, not just binary, like malarial, infected, and uninfected is binary example. Here, this is multi-example where you have barn, you have dog park, landscape, and sunset. So let's work with this. So binary would become a subset of this. Okay, let's jump in, and I would like to start by showing you the way I structured these images. Again, I downloaded these images from my random search, so I cannot share them with you. I don't own them, but you can do a quick Google search and then download a bunch of images for your own training purposes. Again, please keep an eye on the copyright laws for these images. You want to make sure that you're not breaking any law while you're downloading your images, or especially when you're sharing the images. Okay, so here I have 2 folders called train and validation, because I would like to use validation images completely for testing. And these images the system will never see as part of training. And in both cases, I have 4 folders, or subfolders, I should say. Train, I have barn, dog park. In fact, I could easily delete these 2. Let's go ahead and do that. I have barn, dog park, landscape, and sunset. 4 classes. In each of these folders, again, I'm using these examples because these are easily relatable whether you're from life sciences, materials, or geosciences. Okay, and it works with anything. It doesn't matter. So I just downloaded a bunch of barn images, and I called this barn, and same thing with dog park. And as you can see, some of the barn can be confused as dog park. This is not an easy task, by the way. And if you look at landscape, some of these landscapes can, for example, this one can be easily a dog park. Okay, so there is some overlap between these classes, but I think sunset is the easy one, maybe at least a somewhat easier one, although some of these images may qualify for landscapes. So we'll see how our algorithm performs on these, and you can see for each of these I have on average about 75 to 80 images per class. Now for deep learning, you need hundreds, if not thousands of images. For this type of approach, usually you get pretty good accuracy, even with a handful of images. Okay, now let's jump into the code. And I try to, I will, of course, you can find the code, look at the link down here in the description. So you'll have the code. So please watch the video, digest the material, and then practice at your own pace. Okay, so this is very similar to image segmentation that we have done. So I'll skip the easy part that, well, or the parts that we have already covered in the previous videos. So these are all the libraries. Again, nothing new. Please, I believe I made a video on almost every one of these topics. Glob, how to read multiple images or how to handle multiple images. OpenCV, OS, also I made a video. Please look at other videos on this channel. Pandas, of course, we made, and scikit-image. So there is separate videos on each of these topics. But let's go ahead and import these. And for now, I'm only importing Sobel as a feature extractor, but you can apply as many as you want. So we'll go down. So let's go ahead and print the list directory right here, images/natural. So you can see it's giving me train and validation, right? So these are the two subfolders. That tells us that we are in the right area. Okay, next, when you randomly download these images, each image comes in different size, and we want to capture all the information into NumPy arrays, so we need to resize them into the same size for better handling. So I'm going to resize everything into size 128, and in fact, for most classification purposes, you do not need high resolution images. For image segmentation, like pixel level segmentation, of course, that information is important. But if you just want to say, is this a dog or a cat, or is this texture 1, texture 2, oftentimes you can downsize the images to a smaller size, which makes your computation a bit faster. Okay, next we are going to capture the image information and the labels into NumPy arrays. Okay, so how are we going to do that? First, let's start by defining a couple of empty lists. Okay, so you'll see that, okay, our list is just of size 0, nothing in there. Then I'm going to walk through every image within the train folder. Okay, only the train folder. I'll do validation later on. First, let's do this one by one. So let's go through the train folder and split this right here. And let's just run these lines of code so you can see what we're talking about. You see, now we have barn, dog park, landscape, and sunset. So this line here, it is splitting the folder name, subfolder names within train, and taking that name as the label, because we want to label each image based on the folder it's sitting right now. So that's exactly what this line is doing. And then for each image inside our image path, in this case, I'm only looking at JPEGs, of course, depends on your image type. I'm going to use OpenCV to read the image as color, which means we'll have 3 channels. You can do it as grayscale if you want. I'm going to resize them, and we are going to append it to the train images list, and finally we'll convert that into a NumPy array. Okay, this should be very straightforward. Again, if you're a beginner, practice this. There is a lot of information within these lines, so just go ahead and practice these. Okay, let's run these lines all the way up to here so you can see how it goes through each image. You see, it's we have the print statement right there, so it's giving us the path of each of these images, and up here you'll see that our train_images is a list of 320 NumPy arrays. So the total number of images we have in all of these subfolders combined is 320, and each of this is a NumPy array. Now we need to convert this list into a NumPy array so we can work with it. So that's exactly what we're going to do next. Okay, so our train images and labels, both of these will be converted to a NumPy array. So immediately you can see that the size here is 320 by 128 by 128 by 3. Okay, so we have 320 images, each image of size 128 by 128, and 3 channels for red, green, and blue channels. That's what the train images array is telling us. And train labels has 320 labels. What do we see when you open it? You see barn. So we have, I guess, about 80 images as barn, and then comes 77 images as barn, and then comes dog park, and then comes landscape, and finally sunset. So these are all the labels. That's it. So now we have a good starting point. Let's do exactly the same operations for testing images, which means now we'll walk through the validation folder and do exactly the same exercise. So let's run these lines of code. Okay, so now we have our train and test datasets ready. Okay, now the system cannot understand what a barn is or a dog park is. So we have to convert them into values 0, 1, 2, 3, where 0 equals to barn and 1 equals to landscape and so on. How do we do that? We do that by doing this label encoder. So within scikit-learn, import pre-processing, and within pre-processing there is a label encoder, and you fit that to your test labels and train labels. Okay, both of these. So let's look at the result once this is done. So now let's just look at train labels or test labels. It doesn't matter. Let's look at train labels encoded. Instead of barn, landscape, you have 0, 1, 2, 3. That's all we are doing. Okay, we're converting, assigning an integer to each of our label. So our system, the computer can actually handle it. Now we have everything ready to extract features from. So before jumping further, let's actually assign these as xtrain and ytrain, xtest and ytest. Now in this example, I'm just saying my xtrain is equals to train images, remember? Wherever we have these train images, and ytrain is train labels. And why am I doing that? Because it's customary to call our training dataset xtrain and labels as ytrain. Now, I'm also doing this to remind you, in case you do not split your data into train and validation, in separate folders. Nothing wrong with that. You just read one data instead of train and test, but then split it right here. Split that into, let's say, 80% as train, 20% as test. It's up to you. But this is where we do that. So let's go ahead and do this if we haven't done that. Okay. And the next thing is normalize the pixel values. If you look at xtrain here, xtrain, these are all unsigned integer 8, meaning the values go from 0 to 255. This is okay to work with, but sometimes what happens is your values are way too much at 255 in one image, but then the other image is not that saturated or that contrasty. So your maximum will be only at 100. So to bring all the images into same scale, it is always a good idea to divide these by 255 so they all bring into between a range of 0 to 1. In fact, a better way of handling this is by doing some sort of a normalization. So or scaling, I should say. So all the images are scaled to between 0 to 1 and also scaled to the maximum pixel value. So instead of dividing everything by 255, you do that for images where the max value is 255. For low contrasty images where you only have max value of 150, just divide by 150. That's called min-max scaler. Okay, please search for it. And I'll cover these in upcoming videos later on, but just giving you heads up on this information. Okay, so now we have normalized this. Now the next step is, if you go back and look at our xtrain, we have 320 images, each image 128 by 128 by 3, and they're all floating point integers. Bulk of machine learning is handling data, working with data. Bulk of any activity is that when you deal with data. So far, all we have done is got our data into a structure, nice structure that's ready for us to work with. Okay, so the next part, I put this in a function because I would like to go through each image and then apply a bunch of filters to it and capture the response into a pandas data frame, move on to the next image, do exactly the same, capture into a pandas data frame, and so on. Okay, so this is the operation we want to do for training images and later on for testing images. Okay, so how do we do that? What are we doing under feature extractor? So I defined a function called feature extractor, and it takes in an input of dataset. Okay, the dataset shall have the shape of xtrain, or any, not just xtrain, but it shall have a shape of the first one being the number of images, the next 128 by 128 by 3, right? So these are x, y, and number of channels. So 4 of these will go in. So that's the input here. And I create an empty pandas data frame called image dataset. This is where I'm capturing all the information. And this is what I'll return at the end of this, once I capture all the information. So when I call the function, it returns all of this. And what are we going to capture in here? So for each image in range xtrain shape 0, what is xtrain shape 0? 320, right? So this is basically for each image in 0 to 320 or 319, okay? Do the following. Okay, what is the following? First of all, create an empty data frame inside the loop for each image. So for image number 1, it starts with empty data frame. And it does whatever it's going to do. We'll discuss that in a minute. And then goes to image number 2, and then it resets the data frame, empty data frame, captures it, and goes back. Why are we doing this? Because we're capturing all of these feature information and then adding that information, you see DF, that information, to our image data set. So again, this is important if you are new to coding. So image data set is outside of this for loop, right? Which means I'm populating that and nothing happens to it. We're just adding more and more data to that. Inside the for loop, I'm creating an empty data frame every time I'm processing an image. And at the end of that, it transfers all that knowledge to image dataset, goes back, resets, does it for the next image, and so on. Okay? Now that you understand what's going on here, let's see what happens down here. So first thing first, xtrain, which is our data set, because I just said xtrain equals to data set. Okay, you can skip this line and change every xtrain to data set if you want. Okay, so and why did I do this? Because I already have written code with xtrain, but then later decided, okay, maybe I should put this in a function. So I didn't want to change any of this, so that's the reason. But otherwise, you can change each of these into a data set. Okay, now. The first thing we are going to do is input image equals to my xtrain image and all of these channels. What is this line doing? Normally, you would say input image equals to cv2.imread and whatever that image is. But in this case, we don't have to do that because we already have xtrain dataset right here with 320 images, each image 128 by 128 by 3. And again, I'm dwelling a bit of time here because this is very important, assuming you're all still getting up to speed when it comes to coding. So here, all I'm trying to say is for this iteration where my image value equals to 0, this input image is nothing but my xtrain where my image equals to 0, and these 3, I want all the pixels, 128 by 128 by 3, okay? And when the for loop continues for the next one, the image value becomes, let's say 1, and now we are looking at the second image, which is image value 1. And then the next time, image value 2, image value 3, all the way up to 319. So the last image would be 319, and all of these. So I hope that makes sense. So my input image is basically this, and again I reassigned it to a variable called img. And now let's start adding data to this data frame. So far we read the image. Now let's start adding values to, populating this data frame called df. So how are we doing that? First of all, what is the best feature in any image? The pixel value itself. If it is bright, it tells you something. If it is dark, it tells you something. So the first feature I'm going to add is the pixel value itself. So that's what I'm trying to do here. Pixel value, what is the pixel value? You just take the image and I'm reshaping it into one vector. Again, because we need to add columns for each feature. So all I'm trying to do here is just reshaping it. -1 means just into one vector right there. And at every pixel value, that's what I'm taking. And I'm adding those pixel values to the data frame into a column titled pixel underscore value. So that's what this is. Moving on to the next feature. Now you can add, Sobel, and you can add a whole bunch of other traditional features, which we'll do in a second. But watch my video about Gabor filters. This is a convolution where you can generate infinite filters using this, because it's just an equation that's function of sigma, lambda, gamma, and kernel size and theta. By changing theta from 0 to 180, for example, in steps of 5, you can generate a whole bunch of Gabor filters. By changing sigma, same thing. By changing lambda and gamma. But then it depends whether your system can handle that many features. For now, I'm just changing theta and sigma. That's it. Please go ahead and experiment. For our pixel segmentation or image segmentation, we also changed lambda and gamma and generated a whole bunch of features. So I leave that for you as a take-home homework to work on that if you would like to really get better at this. So all we are doing is, okay, we are changing theta, sigma, lambda, and then we are generating a Gabor kernel, which is nothing but we are generating a digital filter. Okay, again, watch my Gabor video to get further explanation, which is a function of kernel size, sigma, theta, lambda, and so on. And once we define the kernel, we are going to apply that. Okay, we are going to apply that onto our image, and reshape the output so we can add it to our data frame right there. Okay, so we are adding it to our data frame and with a column name as our Gabor label. And again, what is Gabor label? It's basically Gabor plus whatever that number of the Gabor filter is, Gabor 1, Gabor 2, Gabor 3, Gabor 4, and so on. Again, if you don't understand this, just take this snippet of code and run it separately, independently, so it makes more sense to you. Okay, so that's that part, and you can keep adding more. I commented this part of code just to show you you can add more things like this, but I don't want to waste the computation, this video time, so I commented this. So here I am adding Sobel filter again, which is an edge detector. So you just apply Sobel onto image, and remember this is the one we imported from our scikit-learn, or scikit-image, sorry, not scikit-learn, up here. Scikit-image Sobel filter, and you can also import char, pruitt, and a whole bunch of other filters. Okay, so I think we're actually done extracting features. Once you do that, at the end of it, I already talked about it, we are appending this new data frame that contains all this information, and then it moves back in the for loop to the second image, does that, and finally, once all the images are done, it's going to return the image data set. So let's go ahead and run this and discuss the remaining part while this is extracting features. So first of all, this is a function, so it's not going to do anything when I run this. So now it knows what to do when I call that function. The next line is calling that function. Okay, how do we do that? We called it feature extractor, and we supply a data set, right? We supply a data, if I can find it, we supply a data set in the shape of what? In the shape of n, x, y, and z. N being the number of images, x and y image dimensions, c is number of channels. So we are going to do exactly that. Xtrain, what is our xtrain? 320 images, 128 by 128 by 3. So this should run fine. When I run this, you see how it's generating Gabor 1, Gabor 2, Gabor 3, Gabor 4, because we have 4 Gabors, 2 times changing theta, 2 times changing sigma, so we have 4 of these, and it goes through these for all the 320 of our images. Okay, this should take a few seconds, not that long. Once it's done, now we will look at how many features we used so we can reshape our images. Again, why are we reshaping this data set? We are the features, because in random forest or support vector machines, whatever you're trying to do, it's actually taking a vector as input. Okay? If you try to put multiple dimensions like 3 or 4 or 5 dimensions through random forest, it's going to throw you an error, and it's going to say it cannot do expecting n dim less than 2 or something. Okay, so if you see that, you know why. Okay, here you go. We have our image underscore feature. So if I go here, you see on the whole we have 3, let's see, 3 and 3, I think 15,728,640 pixels and 5 columns, right? If I open this, it says, let's not open because that's way too many of it. So let's not open right now. So the total number of rows that I have here in the image features data frame is that many, 15 million, and 5 columns. Why 5 columns? 1 column corresponds to the pixel value itself, and 4 columns corresponding to Gabor 1, 2, 3, and 4. Okay, and all those 320 images, I bet if you multiply 320 by 128 by 128 by 3, you get that number. Okay, we may as well check it. 320 multiplied by 128 times 128 times 3 is 15,728,640, right? So this is every pixel in all of our training images. Okay, but we need to reshape this, and I'll show you why in a second. Let's go one by one, okay? So the number of features. First of all, we know that number of features is 5, but let's capture that as a variable. So my n features is 5 for now. If I scroll down, you'll see my n features is 5. Why am I doing that? Well, we'll later expand this into a separate shape, but for now, let's focus. Image underscore features, I'm expanding the dimensions of this along axis equals to 0. If you look at image features, it's these many. Now I want to make it 1, when I say axis equals to 0, it's going to insert a 1 before it. So let's run this so you can see it. Okay, so now you can see my image features shape is 1, 15 million so much, and 5. It's nothing tricky here. I'm doing this one because now I want to divide this array into 320 because we have 320 images. So instead of 15,728,640 by 5, I want 320 by whatever that is. Okay, so that's and 320 because I have 320 images. Okay, so now we are going to reshape this. You see the image features, which is the one that we have, to this specific shape. In fact, we may not even need this n features. I was experimenting with something, but let's leave that as is because I'm going to use it later on. So let's reshape this, and hopefully you'll see what we mean in a second. X for random forest. You see up here, X for random forest is basically 320 images by that many features, you can call it, or these many, so basically we divided this data, 15.7 million multiplied by 5 into 320 multiplied by this. That's pretty much it. Now, the reason why I'm doing that is if you look at our Y train, we have 320 because our labels correspond to each image. I have to match the dimensions of labels to this dimension of features. Okay, that's exactly why I did that. Okay, so again, if this is confusing, please practice this over and over and then try to digest this information. We are basically set to do our random forest classifier. Again, our X for random forest is 320 by 245,760. Okay, if I have any more dimensions, random forest is going to throw an error. So now let's go ahead and import random forest from scikit-learn, and then random forest. Let's start with 50 estimators, which is 50 trees for this random forest. And now I just defined the model. Now I need to fit it. Random forest fitting is very fast. Now, if you want to use support vector machines, you can. I'm leaving the code right here. Instead of random forest, all you need to do is import support vector machines and go ahead and test it. Now, I provided this argument down here, decision function shape equals to OVO. Look at support vector machines documentation. They'll talk about for multi-class classification, how you can use this, or you can use svm.svc, which would make it a one classification against others, because by default support vector machines is basically one classification, right? Binary. You have either one class or the class 2, but in this case we have multiple classes, so you can do one versus the other. Okay, again, this is not in a support vector machines tutorial, but at least at a high level it makes sense to you. Let's go ahead and fit the random forest model for now. And you'll see that this is, even for that amount of data, very fast. This is what I like about traditional machine learning. It's unlike deep neural networks. I don't need to train this for days and days and days. Of course, we'll look at how accurate this is going to be, especially I'm not using that many features, only 5 features, pixel values and something else. So I'd be very surprised if we get anything above 60% or so accuracy, but we'll see how we do. Okay, so we have a model now. We just need to fit that, we have a model that we already did fit. Now we just need to start predicting. That's it. So the best thing to predict on is the validation data, because we know what the right answer is. So let's do that. So the test features, again, if you remember our X-test dataset, what is our X-test dataset? It has 20 images, each 128 by 128 by 3. Okay, so we need to extract same features. So I'm going to apply feature extractor here. And you see how it's extracting all the features. We need to do exact same pre-processing, which means expanding the dimensions and reshaping it. So after this operation, my test for random forest has a shape of 20 by 245760. Okay, previously we had 320 by 245760 because for training we had that many images. For testing we have only 20 images. Okay, so now that the shape is correct, let's go ahead and predict it. Okay, otherwise again it says the shape is not right. So let's go ahead and predict. There you go. And if you look at test prediction, these are all the predictions. Obviously that's wrong, right? I mean, that's supposed to be 0. And I already see some of these as wrong labels, but Sunset seems to be doing pretty good. But let's but 0, 1, 2, 3, we don't know which one belongs to what. So let's perform reverse transform or inverse transform. What do we mean by that? Well, I hope you still remember, because we covered about 20 minutes ago that barn and landscape is not appropriate for computers, so we transformed it using scikit-learn preprocessing label encoder. So when you do dot transform, it transforms it from barn to 0. When I do inverse transform, it goes from 0 to barn. That's exactly what we are trying to do down here. So where are we? Right there. So test prediction, inverse transform. So now let's look at our test prediction after this. And you see now barn, landscape, dog park. So there are some mistakes right here, and we'll see how good the accuracy is in a minute. Okay, so that's done. By visual inspection, yes, it looks like some issues going on, but let's actually print out the accuracy. Okay, the way we are doing that is within scikit-learn, we have metrics that we are importing, and within metrics, accuracy scores, which takes 2 arguments, truth and prediction. So our truth is the test labels, right? These are the original labels, and prediction is test prediction. And looks like our accuracy is 0.7, 70%. That's not bad. In fact, we can make it better. I know it was better when I added Sobel. In fact, when I added a couple of lambdas to the features, so more features describing the image, so you get much better accuracy. So I'll leave that to you, but there you go. That's how we got 70%, which is not bad. Now let's print the confusion matrix, okay? And within scikit-learn metrics, there is something called confusion matrix. Go ahead and import it, and let's calculate it. Confusion matrix is basically on each axis you have barn, dog park, and the other axis you have barn. How many images of barn are misclassified? How many are classified correctly? Okay, this is what confusion matrix is. And once we plot it within cbarn, there is a heat map. Once you plot it, please watch video on cbarn if you don't know what we are talking about here, or you can use plot. But there you go. So it's saying that my 3 out of 5 are correctly classified for that class, and 2 are misclassified as class, whatever that class is, class number 2. Same thing, 3, 3, and 5. All 5 of my sunsets are correct. So with these ones, we are getting some misclassification going on, and that's understandable because these 3 classes, the images look very similar, and we don't have many classes here. Many features here to distinguish between them. Again, please add more features to see how this changes. So let's test this on a few of the random images from our test images and to see where it fails and where it is working. So for that, I'm using import random, just generate a random number between 0 to how many ever images we have, 19, and then show me the image and do exactly the same operations of pre-processing and predict it and show me the prediction. Okay, so let's go ahead and work on a couple of these. So that looks like a barn to me. What did it say? It labeled it as landscape, okay? And the actual label is barn. Let's run this one more time. So it generates a different random number. So that looks like a sunset. Okay, it got it correct because it got all sunsets correct. And the next one, barn, it got it correct. The next one, barn, it got it correct. By the way, if you wonder why barn is blue and not red, we are using OpenCV to import the image, and we are not converting it into RGB because OpenCV reads images as BGR. So your blues are red, reds are blue here, okay? But we're not, for classification doesn't make much of a difference or any difference. So here again, landscape correctly classified. Sunset correctly classified. Again, that was supposed to be a red image, but blue right now. Sunset correctly classified. Landscape correctly classified. Sunset correctly classified. So you got the point. So this is how you can design your own image classification. And again, if you get into deep learning, you can get into much more fancy stuff, but oftentimes the simple stuff can be very useful. I've used this approach for texture segmentation of geological materials, and it works amazing. Of course, I did add a whole bunch of filters because I was doing that not just on my laptop, but on an actual real system that has much more memory than just 4 CPUs that I'm using right now to record the video and also to do the computation here. So as usual, I hope you really liked this video and learned something new. And in the next video, let's learn something else. But please do subscribe to this channel please sign up for appear.com account, because a lot of this code, we have those as modules, and you can use them as ready-to-use modules or create your own modules. But please subscribe. Please sign up to Appear. Thank you very, very much.